today we are at our second meeting of the Asia-USA Seminar Series by USACM. And today we have two fantastic speakers, Qianxiao Li from NUS, Department of Mathematics, and Oliver Schmidt from UCSD, Department of Mechanical Engineering. So we'll start on the Asia side with Qianxiao Li. The floor is yours.
Okay, thank you. Thank you very much for the introduction, Gianmarco, and thank you to the organizers for this kind invitation. Very happy to participate in this great event. So I'm Qianxiao Li from the Department of Mathematics at NUS. Today I'm going to talk about some work on in the intersection of dynamical systems and deep learning. In particular, how do we use machine learning, deep learning to discover certain things about dynamical processes? So, of course, modern dynamics is certainly not a new problem, right? So, in some sense, you can think of this as a solved problem, right? So, we have the Schrödinger's equation, for which we can calculate, essentially most quantities we're interested in principle. But of course, we know that the calculation of it is very difficult, right? So, this is a quote, probably overused quote from 100 years ago, say that essentially all of the laws are known. It's just to solve some PDEs, and then we can't do it. And I think after 100 years, we're still in the same stage that we still can't do this. So, what we can do, we can try to, change the problem a little bit. So here I want to discuss how we can learn macroscopic dynamic processes, which means that instead of resolving macroscopic coordinates, for example, if in the room you're in right now, there are air particles in the room that are moving, high velocities and so on. We suppose that we only care about, let's say, the pressure that the particles are exerting on the walls of the room, then it is not necessary to resolve all the positions and velocities of each individual molecules. Instead, we can try to find some closure equation. For example, coordinates like volume, number, temperature. So these are just 3 dimensions. And together, we will form a complete description of the system in terms of these coordinates. And you have some thermodynamic equation that closes the system. So this is why these are called the closure variables. And these are very important and very useful. So for example, if you want to increase the pressure in the room, this tells you that you just need to increase the temperature, right? Because this is one way you can try to control the dynamical process. So this kind of description is already very useful. And the goal of today's talk is to talk about how we can discover or learn such descriptions from data. So we know that for dynamical processes, if you want to find the right kind of closure coordinates and also to construct this macroscopic dynamics, is certainly a non-trivial problem, right? And I'll give you an example in terms of polymer dynamics later on. So the goal is to ask whether we can use machine learning and data science to automate this process, right? To finding the closure variables and the thermodynamic description, the macroscopic dynamic description of the system. So what is the mathematical formulation of this problem? So we're given some microscopic degrees of freedom. This xt is a very high dimensional vector, right? Which we do not want to resolve. But we're given some observations of it. And our goal is to learn a macroscopic dynamics for a state, Z star, which is a very low dimensional state. So this is a deterministic transformation of your microstate. Okay? And the goal is to model its evolution. So this D1 is much smaller than D. And we aim to find two things. One is closure variables. So some other coordinates that are also of low dimension in nature that closes the systems to make that so that we can together form a hopefully Markovian dynamical model for the evolution of this macroscopic coordinate ZT. So ZT is the macroscopic description of the system. So previously, this could be the pressure, Z star, and the other ones will be the temperature and number and so on. Okay. So one example of interest is the following problem. So this is a very classical problem in polymer rheology. So if you have a long polymer chain and you put it in some fluid and you just suspend it there, what happens is it will coil out. Okay. And people are interested in, if I were to apply a force in the horizontal direction to stretch it, how would the coil respond to such a force? Now, from a physics viewpoint, you can imagine the following argument, right? So if the force is not strong enough, nothing really happens. And if the force is sufficiently strong, the coil will start to stretch. And once it starts to stretch, these restoring forces may become weaker. Okay. And if for example, it's electrostatic or some other forces. And if it becomes weaker, it should continue to stretch. So from this argument, one would expect that this stretching will happen abruptly, right? If the force is sufficiently large, okay, then the the polymer will stretch, and otherwise nothing will happen. But what happens is that what's interesting is that when they did experiments to measure this line is the mean length of these polymers as a function of how much you stretch it, increases not abruptly but gradually. So that was very puzzling. And these two papers actually try to resolve this problem by looking at one single polymer. And what they observe is that every single polymer does stretch very abruptly. So you can see on the right-hand side, each of this curve is a time versus the extension. So you can see nothing really happens, and then suddenly stretches. But what happens is all of these polymers stretch at different times. So there's great heterogeneity in the system. So when you average them, you do get a bulk measurement that is gradual. Okay, so they sort of resolve this problem. But of course, what is not known, at least quantitatively, is why is there such a big heterogeneity? How do you describe this dynamical heterogeneity in the polymer stretching process? So for this example, xt will be the coordinates of each constituent molecule, small molecule in the polymer chain, so this node. So this is a very high dimensional object. But what we care about is not the position of each individual molecule, but really we care about the length or extension of this polymer at time t. Okay, so this thing that you're measuring on the right y-axis. So this is really a one-dimensional macroscopic state that we care about. Okay, so that's one example. Okay, so we're trying to use machine learning to learn dynamics. So of course we should talk about how we should do that. Now, so remember these macroscopic coordinates, right? So if we were only interested in prediction, so of course for stochastic system, this is a reasonable thing, right? So we can say that dz dt is just f of z, where f is a neural network plus some noise, and we just fit this neural network to data, whatever it is, right? If your favorite neural network transformer or whatnot. However, I'll argue that this is not very useful because often we know more about the system than to just use the black box as a surrogate model. And in fact, more importantly, we're interested in more. We're not just interested in prediction, right? We want to be able to use prior knowledge to constrain the kind of dynamics we can learn. And not only that, after learning, we are not only interested in prediction, we want to be able to analyze the dynamical landscape. For example, can I, query like why is it that some polymers stretch faster than others? What does the dynamical landscape look like? How does it depend on the amount of force I apply externally to the system and so on? So what we want is really a structured and interpretable hypothesis space instead of a general black box. Okay, so in some sense, this approach is a classical one, right? If you think about how we build mesoscopic or macroscopic models classically, this is the way, right? We observe, for example, ionic magnet dynamics. Right? This is Glauber dynamics, for example. And then we can say, okay, let's guess that we have a model of a PDE model for this evolution. And then we have some parameters. So this is the usual Alan Kahn PDE model, or 5-4. And we can fit all these parameters, okay, this in this case 4 parameters to a few data points, and then we get a very good model. Okay, but the limitation of this classical approach is that it requires really strong physical knowledge. We must be able to write down some equation that makes physical sense, right? And it's not easy to guess. I mean, it's probably easy to guess for the Ising model, but it's not easy to guess otherwise. And the another thing is that we can only deal with very small parametric models because when the number of parameters get very large, like in liquid crystal models, then it's very difficult to conduct experiments to fit them. And of course, one big issue is that they are only qualitatively accurate. So they only describe qualitative phase transitions. So this is like kind of Landau's model. But they cannot tell you quantitatively how the dynamics proceeds. And of course, there's a lot of mathematical computational issues like numerical analysis, mathematical issues like well-postness of the equation. So those are big problems. Now, what does modern machine learning bring to the table that's different from classical model building? So I will argue this is 3 things are very important. The first one is that we know now that neural networks are very efficient, high-dimensional function approximators. So instead of like using Fourier basis, these things really work in very high dimensions. That's first thing. And second thing, so in other words, we can approximate unknown functions well now. And the second one is we are allowed to take, calculus on these functions automatically. So we can now say that I can parameterize a function v, but I will use it in terms of its gradient v. Okay, so this is also very useful for model building. And third is that we have a lot of data. So with that, I think there's this new way arising from the current literature of another way to build the model, which is instead of guessing a model with undetermined parameters, we guess the model class, the class of model with undetermined functions. So I'll give you an example in this talk. And instead of fitting these parameters, because we have a class of models with functions, we try to fit the functions and ensuring some correct structures. And with this, the advantage is that well-postedness and numerical stability is ensured a priori, because this function class, this model class will have these properties. We'll build it into them. But of course, you sacrifice something, is that instead of having a priori good physical motivation, like Landau's model for phase transition, now you have to do physical interpretation a posteriori, because after learning this, your dynamics, then you try to see, okay, what you have learned. Okay, but I think this is a nice new way to model dynamics that we should explore more. Okay, so this particular case study, I'm interested in dissipative dynamical systems. So here's what we propose. We propose a generalization of the Onsager principle for the linear response kind of near equilibrium regime to learn the following dynamics. So again, we have an equation which is in the form of z dot is fd plus noise, but it has this f has some structure, right? So here, this f is driven primarily by the gradient of a potential function or a free energy function v. Okay, and M is the symmetric positive definite matrix that models the nonlinear kind of non-equilibrium dissipation, okay, of of energy. And W, it measures this entropy production or these so like these rotational forces in the field. So W is the anti-symmetric one, and sigma is of course usual non-isotropic multiplicative noise. So this is a very highly general set of the model class. Okay, so this is the model class, and M, W, V, and sigma are known functions. They are parameters. They're functions. Okay, so with this, maybe I'll say a few words about why this is the good hypothesis space. Well, the first one is it really generalizes the Onsager's work for near equilibrium processes, and we can recover it in some special case. The second one is it always dissipates energy, so the mean energy always decreases until about thermal fluctuation level. You can prove this. So this ensures that the dynamics is in principle stable. Okay, so stability is ensured a priori. And finally, this is the important point for our application of closure modeling or coordinate transformation, because we are trying to transform from a microscopic coordinate xt to a macroscopic coordinate zt. So what this result basically says is that if your xt follows some dynamics like this, which is very general, then after a coordinate transformation, zt will follow again this dynamics, but with different functions, v, sigma, and w. So this space is closed under coordinate transformation. So this is not true, for example, for simple gradient flow. Okay, so let me summarize the workflow, and I'll talk about a little bit about the experiment on polymer dynamics. So here we are given some macroscopic coordinates, and we are interested in the macroscopic dynamics of Z star. So we will have two kind of machine learning components. The first component is a neural network that tries to learn the closure coordinate Z hat. So this is again a lower dimensional coordinates. And we will concatenate these coordinates together to form this coordinate space Z. Okay, this is very low dimensional again. And then we use the stochastic Onsager principle to constrain the hypothesis space for this dynamics, and we learn all these unknown functions from data. Okay, so this is the approach, fairly general. So let's look at the case study for polymer dynamics and what we can do with it. So there are many interesting questions we can ask, right? For example, can we accurately predict the dynamics of your extension, Z star, how fast this polymer is stretching? And what are these closure coordinates we learn? And what can we learn about the dynamical landscape, right? So this is perhaps the most important one. So we'll train our approach on two closure variables. So this we have a three-dimensional dynamical system. And the data we're going to use is from coarse-grained molecular dynamics simulation, so the beat-the-rod kind of model. And then later I'll show you some experimental data. So after training, we can show that, we can really predict the statistics of the unfolding, right? So on the y-axis, so each row is a different polymer sample that's not seen before. And although these are just stochastic runs of that polymer, and we can see that we can predict the mean extension. So Z1 is the extension, how long the polymer is. We can predict its mean, its standard deviation fairly well. And moreover, this is the most important one, is that we can predict how long it takes for the unfolding to happen. So for example, the first one unfolds very quickly. Okay, so this is a very sharp distribution. but the last one unfolds fairly slowly. Okay, so this one has a very gradual distribution. Now, and later we'll see why this is the case. So we found two closure coordinates, so it will make sense for us to ask the question, what do they correspond to, right? So this is again a kind of post hoc kind of analysis, a posteriori analysis of what they mean. So here, what we can see is we make use of the fact that our macroscopic coordinates can be differentiated. Okay, so this is important because after you take, for example, Z2, which is the first learned coordinate from our network, we can take a polymer configuration X and add and subtract the derivative of dz dx. So this basically asks, in what directions should I move this polymer to effect the greatest change in my learned coordinates? Okay, so these two are the configuration changes. And you can see that what's changing is the shape is mostly the same, but what's changing is the end-to-end distance. It's very different. So we hypothesized from this little experiment that what we learned, it might be highly correlated with the end-to-end distance. And we can look at this plot and see that, yeah, they are highly correlated. Of course, they're not equal, but they're correlated. And similarly, we can show that the other coordinate that we learned is highly correlated with the so-called folderness of this polymer. So this is not, so end-to-end distance is a very well-known description of polymers, but this folderness is not as well known, at least in our knowledge. So, but we can discover that there's another measure of how folded the polymer is, and this is related to our new coordinate. So in other words, as long as we know how long the polymer is, what is end-to-end distance, and how folded it is, these three coordinates are enough to govern its dynamics. Okay, so this is something new that we can learn from this analysis. And then we can then visualize the dynamical landscape as what we set out to do initially, right? So we can see that what happens is, interestingly, this landscape has two global minimum corresponding to the head and tail symmetry of the stretch state. Okay, so this is totally flattened. But what happens is that the slow trajectories that we observe always pass through this point. And if we use, some optimization algorithm like BFGS on our dynamics, again, we have a differentiable landscape, so we can do all of that. And we look at the landscape, the potential that we learn, and there's a settle point here. Okay, so maybe it's clear to see. There's a settle point here in our potential landscape. And this will mean that it's really the settle point stable manifold is attracting all of these slow trajectories. Okay, and we can confirm that with the simulation. So this is a settle point, and a slow trajectory will get attracted to this settle point. And this settle point really roughly corresponds to a state where the polymer is folded in half. And this is in some sense, there's a neutral direction horizontal. There's a stable direction horizontally and an unstable direction vertically that you have to escape from this settle point. And this is why some of the or many of the trajectories are actually slow. Okay, so from here you can learn a lot about the system. So let me say one more thing about what we can do. So, for example, we can also so because our potential landscape V, right, a potential function is a differentiable function. We can take its derivative because we can use autograd. We can do the following. So at the stable state of the stretch state, we can do a Taylor expansion, right? We can use automatic differentiation and do Taylor expansion and get these coefficients. And we see that the change in the energy around my steady state will correspond to the change in my learned coordinates in the following quadratic form, right? This is just the first order expansion. The first order, of course, disappears because of the steady state. Then we can then draw this level sets as a quadratic form to see how these coordinates are correlated with each other. So we can see that now Z1 and Z2 are very correlated with each other. Okay, so this you can think of as a partial equational state, which says that if I give you some temperature perturbation, KBT, then that will be, give you some enough energy to get a change in energy of all the delta V. So KBT should be proportional to the changes of these coordinates, right? So this is like a partial equational state, and this is a concrete prediction that from our dynamics that we can try to verify from experiments. Okay. So what we can do here is to conduct some experiments. My collaborator has set up a microfluidic device where we put a DNA molecule in the middle and we stretch it with the electric field. Okay, so DNA is negatively charged, so you can use the electric field to enact this kind of stretching force. And here are some experimental data. This is an actual image get from this DNA. So you can see that some of the polymers does stretch, get stuck here, okay, stretch slowly, where some of it is very fast. And now we can take our learned potential or dynamical landscape and try to verify some qualitative features. Again, we're trained on molecular dynamics, so we can't be quantitatively accurate for a DNA molecule, but qualitatively, we can see some agreement. For example, we can show that after projection to the reduced coordinates, the actual slow trajectories do, in fact, get stuck in our simulation from the initial condition given from the experimental setting at our settle point more than the fast trajectory. Okay, so in other words, qualitatively from a landscape, this fast and slow trajectory in real life do live on different parts of this landscape. And finally, we also, just now we have this partial equational state. And we show that this Z1, which is a stretching the extension, Z2, which is the end-to-end distance, they are highly correlated, right? And they are correlated in a non-trivial way. And we show that the same correlation is actually observed after normalizing by the length in experimental data. So this source 1 is from our experimental data, and source 2 is from a previous experimental data on the same setup after rescaling. So there's some interesting qualitative things you can learn about the system that holds across the board. So we have the implementation of this approach is general, right? It's not just for polymers. So if you're interested in trying to model dissipative dynamics of whatever system you're interested in, we have a hopefully user-friendly way to do that. So you can take a look at the documentation to find out more. Okay, so maybe I will say one last thing. Is that one crucial remaining question is the problem of identifiability. So previously, we are really trying, mathematically, we are looking at trajectories of V, so this dynamics in the macroscopic scale. And we say that we can identify our functions, for example, in particular, the energy function V, right, from this. The question is, you may want to ask is, okay, if I give you the distribution of my trajectories, is it always true that they can uniquely determine these functions? Okay, this is very important. The uniqueness is really important if you want to compare what you learn across different settings. For example, I'm going to learn different models across different temperatures, different external conditions, and I want to see how the landscape changes as a function of temperature or external conditions. Right? This is not what we did before, but this is what we are doing now here. But to do that, to compare them meaningfully, you really need to make sure that these are, in some sense, unique. Right? Otherwise, you have a problem. So the previous formulation of Onsager principle it's actually not unique. So there are gauge issues. So you can pick a gauge for V that will change M and W, but it will give you the same dynamics. So what we show here is that if we do a principal modification of this Onsager principle and based on compose decomposition, then we can actually give rise to not only universal but identifiable distributed dynamics, which means that all these quantities can be uniquely determined. So the idea is basically to use the fluctuation dissipation relation to constrain my fluctuation term sigma, and also to add this divergence term, so to make sure that my V is really the unique, characterized a unique invariant distribution of the system. And finally, our antisymmetric part needs to have some banded structure to ensure the uniqueness. Okay, so this is done in the recent preprint of ours. So if you're interested, you can take a look at this, where we use this to study phase transition and entropy production. Okay, so with that, let me conclude. So there's a lot of algorithm kind of research that we can also do. I will not have time to talk about it, but to learn this dynamics, you have to overcome. If you want to work on actual systems like particle systems or images from experiments, you really need to know how to learn from partial information, whether it's coarse grain in time or coarse grain in space. You need to learn from different modalities like image and video data. You have to try to combine physics-based model with data-driven model in some non-intrusive way. And also, after you have some machine learned dynamics and you want to do numerical simulations, you also have some problem with stabilizing the simulation. So we have done some work on that. If you're interested, we can discuss. So thank you very much for your attention. Here's your some references if you're interested. Hopefully,
thank you, Qianxiao. Amazing
time.
talk. Yeah, very nice talk. So I think for the format of this seminar series, we go straight to the second talk and we confine Q&A at the end. The second speaker is Oliver Schmidt from UCSD. I will leave the floor to you.
Okay, great. All right, so my background is very different. I'm a fluid mechanicist by training, just like John, arguably, who invited me. So thanks you for this, and thanks to Pablo for organizing. Well, for me, it's still the second. I want to talk about, more of a classical statistical method. So you're going to get a nice variety today. And that is a data-driven forecasting technique. So that we have in common. But it's for prediction. It's for forecasting complex spatial temporal data like turbulent flows. So this is an example here. This is a measurement data. You see it switches from a hindcast in black and white to a forecast in red and black. So that's what I'm going to talk about. The flows of interest in this talk are either stationary flows. So what I just showed you, and I'm going to show you that data later. That's by my collaborators out of Illinois. That's particle image velocimetry. That's a flow field of the flow inside a cavity. The flow goes fast over the top, and it recirculates inside that cavity. So red is fast from the left to the right, and then on the bottom it goes back. So that's a stationary flow. Time-dependent stationary flow. So stationary that has a well-defined mean and variance. But we're also interested in transient flows. And a good example of a transient flow is an explosion, right? So that does not have a well-defined variance and mean. Well, it does, but not in the long-term time limit, but in the ensemble sense. So what I want to start talking about now is proper orthogonal decomposition, in particular the space-time variant of proper orthogonal decomposition, because that's the machinery that's under the hood of everything I'm going to show today. And then I'm going to just show you just two examples of things we just did with this technique as basically a post-processing technique on steroids, some physical exploration and engineering example, and a fundamental flow physics example. And then I'm going to talk about how we can use this for prediction. So I'm going to walk you through, just in pictures, through the linear algebra here. All right, so we're given spatial temporal data, and I always imagine this or just visualize it as a video. All right, so we have a number of, call them snapshots, that can be 1D, 2D, 3D, and then we have many of those a time sequence. So the first thing is we flatten these into one long vector, and then we stack many realizations, as many as we can get, into a big data matrix. And then it's classical. It depends on your background, right? When you're fluid mechanics, you call it POD. Everybody else probably just calls it proper orthogonal decomposition. Then maybe, John, you have to remind me what they call it in geophysics, something empirical modes or something. I forgot. So this is how you compute it. In the end, all you have to do is you form the autocovariance matrix of your data from your data matrix, and you compute an eigenvalue decomposition. You can solve. I'm solving the small problem here that's sometimes called the method of snapshots after Zerovich. You can solve the large problem. It's just more expensive, right? Because just imagine you have a three-dimensional flow field that already has a million degrees of freedom, and now you stack, I don't know, a video of 150 frames or something, right? So this is a lot of degrees of freedom. So this is just the smaller problem to solve, but you can solve the larger problem and then just linear algebra, the right singular, the right eigenvectors if you need them, or the left eigenvectors, or you can just solve that singular value decomposition right away. It doesn't matter. So in the end, all we need is an eigenvalue decomposition of this. Now it's a realization correlation matrix. It's 2.2 space correlation matrix of these realizations we stacked into this matrix. And from this, we can construct the POD modes. They have all of these nice properties, right? They're all orthogonal, and they're optimal in terms of variance. Or if we kind of embed this into a nice Hilbert space with properties we like, then in terms of an energy. And there are still videos, right? We can animate those. We can, reshape these into our original data shape. So there was the original. That is the original. That's kind of the motor of the whole thing. So how do we get that ensemble in the first place? Well, for a transient process, it's obvious. When we have an explosion or something, or a polymer unfolding, we just run that experiment many times, and that gives us our realizations. If we have a stationary process, then usually we just chop our long data. Either we rerun the experiment, that's an option, or we just chop it, we just segment it into many segments. And if we're looking at something that is events, extreme events, or kind of other events, then we have to condition. to get these realizations. And I'm going to show you two examples of this, physical examples, and then we're going to talk about prediction. Here's number one. That's an engineering example. This is about aeroacoustics. It's about how a jet generates noise. So on the top right here, that's the jet. This red to blue here, that's fluctuation velocity. So that's fully turbulent. The nozzle is in the simulation. I'm not showing it here. It's three-dimensional, but we're only looking at the first azimuthal mode. That's the loudest, right? And we can decompose it because it's a cylindrical system, no loss of generality. And in the background here, the black and white, that's the pressure. All right. So if we take the data at some location here, and we compute, for example, a wavelet transform, we're going to see something like this, right? At some frequencies, so this is frequency, is non-dimensional frequency here, Strohal over time, we can see this kind of loud, the burst event, right? This loud pressure fluctuation. If we look at a time where we don't see any of these kind of black spots, then the field looks like this, not much happening. And here we have this kind of burst event. That's kind of also interesting in the sense that prediction models for jet noise, they were always missing the actual jet noise by 5 dB or something, which is not acceptable. And this is because they were all kind of statistics based. But the way that the noise actually occurs, that it looks like in nature, it's actually in terms of this kind of loud burst. So how can we use the space-time POD to analyze this? We just put this is an animation. I hope you can see this. That never really works well on Zoom, right? So this is an animation, and this is just the time trace at this probe location, and this is the corresponding histogram, right? So it's highly intermittent. So if we compute a POD, a spectral proper orthogonal decomposition, then we just get the average most energetic coherent structure associated with this. And you see it's this beautiful acoustic beam, only that in reality, you never see this. This is the statistical object. This is exactly like Qianxiao's mean of the polymer, right? So this is a statistical object. You shouldn't interpret it. It looks beautiful because it's smooth, because it's a statistic, but it's not physically meaningful, right? But if we condition just by thresholding, so whenever we get a high peak up here, we threshold, right? So then we get the tail of this distribution, right? Then we get these kind of burst events that are much more physical. And now to compute the space-time POD, we're gonna define a little environment, a neighborhood in time around these events. And then we're going to stack these in the matrix. We all make them the same length, of course. We stack them in the matrix. And then we can compute the leading mode. And it takes this form at a specific time. But the mode itself depends on time, right? So now we see the same thing swimming out. But what's kind of cool about this is that we can, of course, define our time interval to go in the past, and we can identify this precursor, right? And that is, of course, implications, because we know if we detect this thing with whatever method we want, then we know at a certain finite time later that we exactly know, because we defined it, we're going to see the acoustic burst, right? So that's just an application. This is, again, the space-time mode, and then not really related to the rest, but interesting, we actually find a linear model that simulates this thing really accurately. That was the first application. The second one is very fundamental turbulence theoretical thing. So this is a direct numerical simulation by Lozano, Duran, and Jimenez. We just got this data, and the holy grail in turbulence theory is for people, well, they want to model it. How do you model it? You have to find some kind of Lego block, building block for your models. So people are always after coherent structures in these things. They want to see, is there small building blocks of turbulence that we can identify, give a name, and that, identify with some physical phenomenon. So here's what we did, is we just took a plane, 2D plane that's shown here, and we're plotting the dissipation. Dissipation is just a really good indicator for just stuff happening. For coherent structures, because that's usually what they do, right? They absorb a lot of energy because there's some kind of underlying hydrodynamic instability mechanism, and then they dissipate it. All right, so now if we look at this thing, we can find some of these, but they correspond to these kind of, hard to identify structure. Probably could convince people that this is a kind of polymer unfolding or something, right? So no idea what this is. So the idea here is the same as before for the acoustic burst. We're going to define a little neighborhood. It's going to swims with the average advection velocity. We run it through the machinery. We separate into symmetric and anti-symmetric. We find one anti-symmetric structure. It looks like this at different heights of the domain. It looks symmetric because we're taking this streamwise vorticity here. So that's impossible, to interpret if you're not like in turbulence theory, which I'm not either. But what this looks like, that's kind of meandering streak structure. So that's a very well-known object in turbulence. But this one is even more well-known. That is called a hairpin vortex. And we just were able to identify this in a fully turbulent flow where you could never, with your naked eye, spot this structure, right? And it even fits. This is just the summary result, just as before, this old hypothesis by Townsend to hypothesize, well, that the turbulence kind of built of these little structures being stacked on each other over different heights. Okay, so that was kind of, just two examples of how just the space-time PUD can be really useful for physical discovery, but also for engineering problems when we're dealing with these with events. The goal for today is just to use this machinery for forecasting. So here's the simplest forecasting problem we can pose. Here's our explosion again. Here's our cavity flow. Let's say we're given n snapshots. We want to predict the next m. That's all there is to the problem. Here's how we're going to do it. That's the same state we saw before, but now we're going to separate it between a hindcast and a forecast, right? So from n snapshots in the hindcast, we want to predict the next m over the forecast horizon. We needed again an entire ensemble of training data. But then the goal is when we're given new data that, of course, only exists over the hindcast horizon, we're not cheating, to make a forecast. So that's the goal. So this is going to happen during an online stage when we do not have any knowledge over the forecast. And in an offline stage, we're going to train. When I say train, there's no machine learning. This is all statistics. So we're going to solve the space-time PUD problem only for the hindcast horizon. This gives us the same thing I showed you before, modes that only evolve over the hindcast horizon. So that's not useful yet. But what we can do is, since for the offline stage, for the training data, we have the forecast horizon extensions. We append them, and then we get modes that are appended to the forecast horizon as well. That looks very ad hoc, and it is very ad hoc, but there's actually a beautiful proof by Boré, 20 years old, who showed in a completely different context that if you do this, then whatever happens here is optimally correlated to what happens here. So we have an optimality property here, even though it looks and sounds very ad hoc. That's the idea. Well, how do we get to the forecast now? Given this new data here, we stack it in a vector, we project that onto the modal basis only in the hindcast, only over the hindcast horizon, because that's what we have. But then we do the expansion into these expanded space-time projection modes that include the forecast horizon, and then we can extract the forecast. That's how the whole algorithm works. So it's very simple, really. Well, what's nice about this algorithm, I would argue it's a really good baseline to compare to more sophisticated methods too, because you really only have one single tunable parameter, right? So this is kind of the problem, the forecast and the hindcast and the forecast horizon and the ensemble size, right? So that is just the problem itself. And the only thing we can really play with here is, well, there's norms and so on, but the only actual hyperparameter is just really the truncation rank. Are we including all of the basis vectors, or do we, for some robustness, to get some more robustness, are we just going to throw out the lower energetic ones? So here are the two examples. So the first one I showed you, the explosion, that's actually a very nice simulation of a supernova explosion. So that's on like very different scales than we usually work in fluid mechanics. So this box is 60 parsec cubed. And this actually simulates the formation of the Milky Way. So there's one sun worth of mass in the center, and it's and the database contains 400 realizations of this thing, of this explosion, and then there's independent data set of 50 for testing. So that's the supernova explosion. And then the second example, that's that cavity flow by my collaborators. Yang Zhang measured this in Luca Rafessa's lab. And we got, it's a beautiful measurement, right? Because this is high Reynolds number. This is completely turbulent. It's two-dimensional and it's ultra high speed. So this is a high Mach number at 0.6, well, arguably high, right? 16,000 snapshots recorded over 1 second at 16,000 hertz. So this is quite the measurement. Here's the spectrum. You see these tones. You can see them. This is frequency wave number diagram, frequency and wave number. Why do I plot frequency wave number diagrams? Well, because, you know, the slope of this just tells us something about the advective speed, the phase velocity and the group velocity, because it's not dispersive, right? Of the waves that travel at this interface line here. And that just gives us a really good idea of, you know, that sets the expectation, right? So we certainly cannot predict above like a flow through time, because then we're saying, well, we're predicting stuff that you know, that the algorithm doesn't even see, right? That doesn't even exist, that is outside of the domain. So that's that data. Well, and these peaks here, they come from an acoustic resonance, right? So we see these instability waves, they're hydrodynamic instability waves, they're hitting the back, right? So there's a wall here where it's blue, that's a wall, this is a cavity, right? Then you get acoustic waves that go back and they form a feedback cycle. And so you get these tonal peaks. These are the two databases, and here are the space-time PUD modes that we're going to use. So this is the supernova. These are two, right? So in total, we have like 59 snapshots each, and also the delta T, that doesn't matter. This actually is between, I think, 110,000 years. The method doesn't care. They just have to be in phase between realizations in the ensemble. And what you can see here, it's kind of interesting that it recovers this like a dipole, quadrupole, just discovers spherical harmonics. You can clean this up a lot by actually rotating the data, right? Because I'm not using the rotational symmetry here at all. So you can make this even better, but I didn't. The first mode, they capture about 71% of the variance of this thing. For the cavity, the modes look like this. The first ones, they correspond to these physical mechanisms that, if you're a fluid mechanics guy, you know what they are. Kelvin-Helmholtz waves. If not, it doesn't matter, right? They're coherent structures. They're very well converged. This unconverged junk, well, that's what we just expect to see in the higher modes, right? So that's everything that kind of doesn't, that is just hard to converge, because it's a fully turbulent, it's a fully chaotic system. 100 modes give us about 80% of the total variance or energy. This is the supernova explosion. This is the actual forecast. So we're looking at 4 realizations. I think I took the one with the lowest error, the highest error, and 2 random ones, right? So to set the expectations, we can never be better than, right? We're restricted to our modal basis, so we can't do better than that. So if we compare over the hindcast, right, we see the structure. So on the left, that is the raw data. On the right, that is the prediction, right? And this is never seen, right? So this is from the test. This is from the test data, right? And you see, if you just compare between the realizations, that it does a pretty good job. That becomes much better if you use the rotation method and do that here of predicting these structures. So it works pretty well. This is the same for the cavity flow, right? So that's not easy to look at. These are hindcast, these are forecast. But if we look at 20 time steps ahead, which is when the structures are basically already out that of the flow field that we're trying to predict, you can see that you can see a certain resemblance. Like the blue, red, blue, blue, red, blue. Of course, you cannot expect them to look similar, because this is completely chaotic. And the small scale stuff, I wouldn't say it's necessarily noise. That's also noise is a measurement, but it happens at time scales that we can't even resolve, right? So these structures decorrelate so fast, there's just no way we can get them right. So when we get these large structures, right? And what I did here is, right, just a quantitative comparison with other methods, right? So looking at these pictures, that's not super helpful. So compared the prediction of the space-time prediction to dynamic mode decomposition, right? That's, I guess, now classic algorithm, right? It's a discrete approximation of a Koopman operator, a linear propagation operator. That just propagates the initial solution forward. So there's no learning involved here, right? We just give it the hindcast data and let it propagate into the future. And that's this dashed line here. What I'm showing here, that's the mean RMS error, the mean overall realizations, all 50 realizations that we have from in the training and the testing data. So that's the DMD forecast, the STP, right? The space-time projection, the space-time POD-based one that's down here. And in the middle here, all of these colorful lines is, I thought it would also be good to compare this to something a little more maybe sophisticated to machine learning technique. And so I just picked a vanilla classic LSTM recurrent neural network. So that one has a lot of hyperparameters. So this is why we see the training loss for multiple, right? So we can vary the number of hidden units. We can vary the depth of the recurrent neural network and so on. But even with a lot of fine tuning, it's very, very hard to beat this I would argue pretty basic statistical method, right? So the recurrent neural network, it gets the LSTM beats it over this intermediate time horizon marginally. And then the STP is marginally better. You can hardly see it at very small times. And then at large times, the STP actually outperforms the LSTM and the DMD. That's far out there. That can't really compete. Okay, so that would be the end. Here's just some animation of the explosion, and this is just something in my last minute that I wanted to make you aware of. That is something that a few people from the AAA group for reduced complexity flow modeling of fluid flows are putting together. It's a community challenge that includes compression, forecasting, and sensing. And we basically do what I just showed you on the last slide. We pick one vanilla statistical method, DMD, one machine learning method. We provide the scripts, and then you can basically use your own tools to beat these classical methods. And challenge one is actually exactly that data that I just showed you. Luca Festa gave that to us. Given 70%, given 70 snapshots, just predict the next 30 and see how you can compete with the reference. Okay, and that's it from my side.
Thank you, Oliver, for a very nice talk as well. And thank you both, Qianxiao and Oliver. And I think now the floor is open for questions. Anybody?
There is a question from UAU.
Yeah.
Also.
Yeah.
Hello. Yeah, I have a question to Professor Li. Yeah, thanks for the fantastic question. I think the part when you talk about, you can guarantee the function identifiability. That's really cool.
Yes.
Yeah, I'm curious that do you have any, like, say, assumption to the functions to guarantee the identifiability? Because intuitively, like, say, if for the function outside the data coverage, no matter what the value is, we cannot. It's difficult.
Of course.
Right?
Okay. Yeah. Maybe let me. Thanks for the great question. So what I mean, I should say what I mean by identifiability. So I will go back to this equation here, right? So, so this equation. What I mean by identifiability is a mathematical question. So given the distribution of trajectories of Z, okay, so that means that I can query the distribution, the entire distribution of paths of Z. Is it true that M, W, V, and sigma are determined uniquely? And for example, V is of course determined only uniquely up to a constant. So here I'm not talking about the data distribution, but I'm talking about the path distribution of this entire stochastic process. So you can see that here there is some obvious problems because, of course, I can multiply this M and W by 10 and divide V by 10.
There's some kind of invariant here.
Yeah. So, of course, that's not the only issue because I can compose V with a monotone function, and we can show that these two will still be symmetric, positive, definite, and this V will be changed. Yeah. So there's a lot of gauges here that you can introduce that will be different. So this is what I mean by non-identifiability. And by identifiability, I mean that given this distribution, if I modify this equation on the right-hand side in the correct way, as we show in the paper, you can in principle identify them given enough of these trajectories. So of course, if the trajectories are only like the in some small compact space, then of course you cannot identify everything outside. Yeah, so that what you said is definitely true, but this is not what we show, of course. Another thing I want to say is that yes, there are assumptions. We are assuming that this dynamics has a unique invariant distribution, in some cases ergodic, right? So that means if you take a long time, and then you will settle in the non-trivial invariant distribution. So this is the assumption that is necessary. So without this assumption, then we have counterexamples that there's no unique decomposition like that.
I see. Yeah, makes perfect sense. Yeah, thanks a lot.
Yeah. Okay, thank you.
Thank you. Any other questions?
I have a question for Professor Schmidt. Now I'm trying to using the original POD to find some coherent structure in turbulence, which coherent structure is important in 2D turbulence. But I think the traditional POD failed to determine the insistence of these kind of structures. Do you think your space-time POD is better alternatives?
Yeah, by insistence you mean probably correlation in time, right? And you can you're absolutely right, and you're spot on, right? So you need to include time, right? And one way to do it is you go in the spectral domain if it's like something that is kind of periodic or statistically stationary, or if it's finite time, then you do the space-time POD, right? So the classical POD that is kind of space only, right? That's 2-point spatial correlation. And you can do a simple experiment, right? Just compute a POD, look at the expansion coefficients, and compute that time correlation. They instantly diverge, right?
Yeah. I think your work inspired me a lot. I will try to do this later. Yeah. Thank you for your talk.
Thank you, Yukron. Any other questions?
I had a question for Dr. Oliver, actually. So the STP, does it, like DMD, does it take advantage of the lower dimensional manifold on which the fluid systems generally evolve? Because in DMD, as you said, we can impose a rank on the snapshots and build a lower dimensional linear operator. So which I would say is kind of makes it easier for computation. So is something like that possible with your STP?
Well, I mean, I guess I demonstrated prediction, right? But I think like the core difference here is why I think you can't really square this. These two is one is actually dynamical systems concept, right? It's Koopman theory. That's DMD.
Yes.
And the other one is a purely statistical. It's all based on correlation, on second order statistics. Right. So if you then want to go to like a dynamical systems description, then you kind of have to go sequential, right? Then you have to slap some other mathematical framework on top of it. I mean, you get expansion coefficients, right? So you get expansion coefficients, and of course you can use those and look at your Poincaré maps and all of that, but it doesn't give you an operator directly or anything like that.
Yes, absolutely. But my question was more in regards to the imposition of a rank on the input trajectories themselves, like the snapshots. If that is possible in STP, like to truncate it to a lower dimension on the input side.
Yeah, of course you can do that. Yeah, you can just, that's just like, but you can do a simple rank truncation.
Oh, okay, yeah.
Absolutely. And that actually reduces the error, right? So that there's some, kind of best practice throughout all of the noise. Look at your vectors. The ones that look nice, usually they are the ones that are well-converged statistics. Include those and throw everything else out, and you're going to get a lower error than including everything. Go full rank.
All right. Thank you. That answers my question. Thank you.
Yeah, Qianxiao, you wanted to ask a question to Oliver?
Yeah, just a quick question. So very nice talk. So I was wondering, for your systems with some degree of chaotic behavior, right? You use RMSE, like a root mean square error. Does it make sense to use some sort of other kind of statistics, like energy spectrum, to really measure? Because I see that all the errors kind of level off. So if I have a chaotic system that reproduces all the right statistics, but it is actually trajectory-wise is different from the truth, then the MSE will level off. But I think I can still get the statistics right. Does that make sense?
Yeah, that makes sense, right? So I mean, spectrum only works for the statistically stationary case, and then you get it right, because it's optimal in terms of the second order statistics. So yeah, you actually get that right. In the for the transient processes, oh god, I keep forgetting that name of that norm where you can basically where you can kind of remove the phase shift error from the whole thing.
Okay. Yeah. So you align the time a little bit, and then
yeah.
I have a question for Prof. Li. It's like Qianxiao on the latent variable. It's like can we scale this variable up to 2D or spatial temporal for problems? Because currently it's like ZT, so the dimension is like only scale up with T. Yeah. However, if we consider higher spatial dimension, will the variable be very large and very hard to model?
Yes, we can. In fact, we're doing it right now. So for the Onsager kind of principle, there is so here is what we call mesoscopic model, right? So you have a model for Z which depends on both space and time. So it's like a field. So yes, we can. So there are analogs of the operators M and W. So instead of matrices, the M and W will become linear operators on these spaces of functions of X, right? So you can write out neural network approximations of those operators and learn them from data. So we're currently doing that.
Okay.
Yeah. If you want to know more, we can chat offline about that. Yeah.
Yeah. Okay. Thank you.
Thank you.
It can be done. It can be done.
Yeah. It's amazing talk. Thank you.
Thank you, Qianxiao. Any final question here?
Yeah, sorry. Once I had one more question for Dr. Oliver. I was just thinking about what you said about this being more of a statistical method, and that reminds me of a paper that came out, I guess, in 2024 about which proved a sort of limitation for the DMD is that its validity is only near, I guess, the equilibrium points and near measure zero sets near the limit cycles. So being a statistical method, does STP kind of sidestep these limitations, in your opinion?
Well, I think it does. You definitely right. Something like an event, like the explosion, that's anything but a limit cycle, right? But I think these are just two worlds, right? So I think what you just said, this paper says in a very complicated mathematical way, is just that the DMD reduces to a Fourier transform. Right, so it can only give you stuff that reoccurs periodically, or that exponentially diverges or decays, right? That's its basic limitation, and then the space-time projection doesn't have that. It doesn't have that.
That is very nice.
But
thank
different
you.
beasts again, right? So
yeah, thank you.
Okay. Well, thank you, Aditya. I think we are over time. So thank you again to the speaker, Qianxiao and Oliver, for their fantastic talks.